Okay, welcome back to the next lesson under complex variable. In this, we are going to be talking about analytic function. In the first one, we have been able to understand how functions of complex variables are, their definitions, and how we can find the coordinates of any function of complex variable. But in this one, we will be talking about analytic function. Suppose we have a function f of z. This function f of z, which is equal to u plus iv, where z is equal to x plus iy. This function of complex variable is analytic if it is defined, and also if its derivative exists at any point z equal to z naught. Don't forget, z naught here is a point. It can be 4, it can be 5, it can be any constant. So we said that if a function of complex variable f of z equals u plus iv is analytic if the function is defined, and of course for a function to be defined, the denominator must not be equal to 0, and if the derivative of that function exists at every point z equals to z naught. Now, suppose we have f of z equal to, f of z equals z plus 1 over z minus 4. We have this function. First, before we check for the analyticity of this function, let's first of all find the derivative of this function. And to differentiate this function, we are going to use the quotient rule, which stated that f prime of z is equal to v multiplied by u prime minus u multiplied by v prime over v squared. Don't forget, the top is u and the bottom is v. So let's quickly apply this formula we have here. We are going to see that our v is z minus 4. So this means that we are going to have z minus 4 multiplied by the derivative of the top, which is the derivative of z plus 1. And if you differentiate z plus 1 with respect to z, we are going to have 1. So multiply by 1 minus u, which is the top, and this is z plus 1 multiplied by the derivative of z minus 4, which is 1, divided by z minus 4 squared. Z minus 4 squared. So this means that f prime of z is equal to z minus 4 minus z minus 1 over z minus 4 squared. So we are going to have f prime of z equals z, we cancel out z, minus 4 minus 1 will give us minus 5 over z minus 4 squared. So first of all, we said for this function to be analytic, it means that the denominator must not be equal to 0. So this implies that z minus 4 is equal to 0. This means that if z minus 4 is equal to 0, that is z equal to 4. Z equal to 4 now is the point z equal to z naught. So this implies that at the point z equal to 4, this function is not analytic at z equals to 4. Because if you see, if we put in 4 here, we are going to have 4 minus 4, which is 0, all squared, which is 0, minus 5 divided by 0, which is undefined. So it means that at the point z equal to 4, f of z is not analytic. Therefore, f of z f of z is not analytic. It's not analytic at z equals 4. So we are going to move to the next one. The next one, we are going to see how we can, all the ideas, how we can draft out something from analytic function. So the next one, we are going to move on to Cauchy-Riemann's equation, how we can apply analytic function. See how we can apply analytic function in solving subsequent. Let's talk about the Cauchy-Riemann equation. We always say that W is equal to f of z, and then f of z is now equal to the real part, which is a function of x and y, plus the imaginary part, which is another function of x and y. If this equation, or if this function f of z equals the real part plus the imaginary part is analytic, it means it must satisfy the following condition. The partial derivative of the real part with respect to x is equal to the partial derivative of the imaginary part with respect to y. And also, the partial derivative of the real part with respect to y is equal to minus the partial derivative of the imaginary part with respect to x. Call this equation 1, and then call this equation 2. So the Cauchy-Riemann equation basically is telling us that if a given function is analytic, then it must obey or satisfy this equation, and this equation is known as the Cauchy-Riemann's equation. So we are going to take the first problem under the Cauchy-Riemann's equation to illustrate this condition. Okay, having taken down this problem, the question here says, if f of z is equal to u of x and y plus iv of x and y is an analytic function such that the imaginary part, which is v of x and y, is equal to 2x minus 2xy. The question here says, find a, the real part, and b, the complete function f of z, which is u of x and y plus iv of x and y. So we are going to solve this problem. We are going to solve this problem. Check this out. We have that the imaginary part is 2x minus 2xy. And now we are asked to find the real part. So for us to be able to find the real part, we need to apply the Cauchy-Riemann's equation, which stated that partial u partial x is equal to partial v partial y, and also partial u partial y is equal to minus partial v is equal to minus partial v partial x. So these are the two equations we are going to use to find our real part and the complete function f of z. So you see that if we differentiate the imaginary part with respect to y, it means that we have obtained the derivative of the real part with respect to x. And also, if we attach minus and multiply it by the derivative of the imaginary part with respect to x, it means that we have obtained the partial derivative of the real part with respect to y. Then we can go ahead and integrate to find the function. So this implies that from this equation, from the real part, which is given as v equal to 2x minus 2xy, differentiating v with respect to x, you are going to have partial v partial x, and this is equal to, if you differentiate x here, you are going to have 2. If you differentiate x here, you are going to have minus 2y. So it means that the partial derivative of v with respect to x is equal to minus 2y. And also, the partial derivative of v with respect to y is equal to, remember, we are treating x as constant here. So it means 2x here is a constant, and if you differentiate constant, you have 0. So if you differentiate y here, you have 1 multiplied by minus 2x, which is the constant, becomes minus 2x. So this means that we have the derivative of the imaginary part with respect to x and the derivative of the imaginary part with respect to y. So let's compare it to the given condition. So this implies that we said that partial v partial y is equal to partial u partial x. So this means that partial u partial x is equal to partial v partial y, which is minus 2x. Minus 2x. And also, partial u partial y is equal to minus partial v partial x. So this means that partial u partial y is equal to minus partial v partial x, which is 2 minus 2y. 2 minus 2y. So this implies that partial u partial y is equal to minus 2 plus 2y, or 2y minus 2. So since we have gotten the derivative of our real part with respect to x and y, then we can integrate using variable separately to obtain the real function u of x and y. So let's continue on the other side. So this implies that partial u partial x is equal to minus 2x. Partial u partial x is equal to minus 2x. So if we cross multiply using variable separately, we are going to have that partial u is equal to minus 2x partial x. Partial u equals minus 2x partial x. To find u, we are going to integrate both sides with respect to x, treating y as constant. So integrating both sides, integrating both sides. This means that we have the integral of partial u equals to the integral of minus 2x partial x. Remember, we are integrating partially with respect to x, treating y as constant. So it means that the constant there will be a function of y, because y is treated there as constant. So if you integrate partially, you are going to have u, but it is a function of x and y. And this is equal to, if you integrate minus 2x with respect to x using the general formula, you are going to have minus 2x to the power of 2 divided by 2 plus a constant. But since we have treated y as a constant, the constant we are going to add will be a function of y. So plus a, which is the constant. I use a as the constant, but the constant must be a function of y, because y is treated as constant. So 2 we cancel out 2. This implies that u of x and y is equal to minus x squared plus a of y. Call this equation 1. Also from partial u partial y equals 2y minus 2. We can also integrate the using variable separately, integrating with respect to y, treating x as constant. So if we integrate both sides, integrating both sides, we are going to have the integral of partial u equals to the integral of 2y minus 2 partial y. So let's continue. We have the integral of partial u equal to the integral of 2y minus 2 partial y. This implies that we are integrating both sides with respect to y, treating x as constant. If you integrate partial u, you are going to have u of x and y, and this is equal to integrating 2y with respect to y. You have 2y squared over 2. You are going to have 2y squared over 2 minus integrating 2 with respect to y. Don't forget, if you integrate any constants with respect to x or y, you just have that variable multiplied by the constant. So we are going to have 2y plus another constant, which is a function of x, because we have treated x as constant. So this implies that u of x and y is equal to 2, we cancel out, we are going to have y squared minus 2y plus b of x. Call this equation 2. From equation 1, from 1, we have u of x and y equals minus x squared plus a of y. This was equation 1. Comparing these two equations, if you compare these two equations, don't forget that u of x and y is a function that contains both x and y. So comparing these two equations, you are going to have that from equation 1, a of y, we have a, which is a function of y, plus minus x squared. From equation 2, we have y squared minus 2y plus b of x. Compare these two equations, you are going to see that b of x in equation 1 is minus x squared, and a of y in equation 2 is y squared minus 2y. So it means that in equation 2, anywhere we see any function of y, it is a of y. And from equation 1, anywhere we see a function of x, it is b of x. So this means that b of x is equal to minus x squared, and a of y is equal to y squared minus 2y. So we can go ahead, any of the equation, either from equation 1 or from equation 2, we can complete our function u of x and y. So this implies that from equation 1, we have u of x and y to be equal to minus x squared plus a of y. So this implies that our function u of x and y is minus x squared plus a of y, which is y squared minus 2y. So since we have succeeded in getting our real part, so we can add it up with our imaginary parts to get f of z as required from b. Okay, let's move to the second one. B, we have find f of z. We have already gotten the real part, but f of z is equal to the real part plus the imaginary part. So this implies that f of z is equal to the real part, which gives us minus x squared plus y squared minus 2y, plus the imaginary parts, we have I. The imaginary part was given from the initial question as 2x minus 2xy. So therefore, f of z is equal to minus x squared plus y squared minus 2y plus I into 2x minus 2xy. y. So this is the function f of z. So thank you for watching this video. In our next class, we are going to move on to harmonic functions.